Third and very important rule is they should have Huckel numbers. That means they should or they must possess this many numbers, that is 2, 6, 10, 14, 18 number of pi electrons in their structures. So the first rule, they have electrons, 2p orbital electrons in their structure. They must be planar or nearly planar. There must be a continuous overlap of pi electrons, and they must possess Huckel number type of electrons in their structure. So these are the important properties for that compound to behave as an aromatic in nature. So these all properties or criteria will be met by the benzene. So benzene is the father of aromatic compound. Next we have seen the two examples, pyridine and pyrimidine, whether they are aromatic or not aromatic. This much we have covered. Now pyridine is behave as an aromatic in nature, but the lone pair of electron which is outside the ring of that pyridine will not be possessing or will not having any rule with respect to the aromaticity, because the three number of double bonds which are there in the inside the ring of pyridine will satisfy the property of benzene ring, or will satisfy the property of Huckel number electrons. So that's why there is no any rule of these electrons to behave as an or to give the aromaticity to that compound. This much we have covered. Next, the explanation of pyrimidine ring. So pyrimidine, in that also they are going to have two number of nitrogen atoms. See, this is the structure of pyrimidine. In this also, one of the nitrogen, or in this also, the Huckel number of electron will be covered by these three rings or these three bonds, that they are going to have 6 number of electrons. So they are, both the compounds are aromatic in nature. So this we have covered in the determination of aromaticity. Now these type of compounds, examples of these compounds, whether they are aromatic or not. Pyrrole. The lone pair of nitrogen gives the pi system of 6 electrons. Now here, this nitrogen is also possessing the lone pair of electron, but the structure itself have 2 number of bonds, that is 2 number of pi bonds. That means one pi bond belongs to, one double bond belongs to 2 electrons. So this structure have 4 number of pi electrons, and this nitrogen will be possessing the lone pair of electron. So these lone pair of electron has taken part in the to become an or to show the aromaticity to that compound. But this is not the case with respect to pyrimidine and pyridine. In that case, the compound or the structure itself having 3 number of double bonds. See, this structure is itself having the 6 number of electrons to show the property of aromaticity, but this is not the case with respect to the pyrrole. Pyrrole is having only 4 number of electrons. Now that time, this lone pair of electrons which is possessed by this nitrogen will take part in the delocalization of electrons inside the ring. So this compound will be show the aromaticity. Now second case, 7-membered ring compound. Second case, the lone pair gives the pi system and offer how many number of electrons? 8 number of electrons. Therefore, the nitrogen should not taken part in the aromaticity of the compound. Now, this is also a similar case with the pyridine and pyrimidine. In this also, the ring is 7-member. Presence of nitrogen is also there. That nitrogen is also going to possess an electron. But as the structure itself covering the 6 number, that is Huckel number in that structure, so this lone pair of this nitrogen atom will not take part in the hybridization or will not take part in the showing the aromaticity of that compound. So this is all about whether the compound is aromatic or not. Now some of the examples of next compound, that is furan, pyran, and imidazole, whether they are aromatic or not, that we are going to check. So these are 5-membered compounds, that is furan, this is the structure of furan, this is pyran, and this is imidazole. In case of furan, oxygen is an heteroatom in the 5-membered thing. Now what happened in this case? This is a orbital picture of this furan. This oxygen is going to possess 4 number of pair of electrons on these oxygen atom. Now in that case, the furan will possess 2 conjugated double bonds. That means 4 number of pi electrons. Now in this case, one of the pair of electron will be involved in the showing the aromaticity of the compound, and one of the pair will not be involved. That means the double bonds which are inside the ring will be utilized for the delocalization, utilized for showing the aromaticity, and the double bonds which are not, they are not involved in the showing the aromaticity of the compound. See, this electron pair is an part of p orbital and will be covered the aromatic state of that compound. But the electron pair which is remaining now, this electron pair is in an sp2 orbital and it is not a part of aromatic state. That means only 2 electrons will be involved in the delocalization, will be involved in the showing the aromatic property of this compound. The remaining 2 will not be involved. So they are going to cover the Hookean number 2, 2, 4 plus 2, 6. So this 2 electrons only covering the electronic conjugated system of this compound, and remaining 2 will not involved in the aromatic state. Now next one. Structure of pyran will possessing a 5-membered ring and nitrogen as an heteroatom. Now in this case, this electron pair is in a part of p orbital and is also a part of aromatic system. This structure we have already discussed. Now we will interested in this. Imidazole will be possessing 2 heteroatoms, 2 number of conjugated double bonds, and both the heteroatoms are going to possess lone pair of electron. Now what is the case with imidazole? In imidazole, the unshared pair of electron on one nitrogen atom is a part of aromatic state. That means out of these 2 nitrogen atom, one lone pair of one nitrogen atom will be involved in the conjugated system of that ring. The lone pair of electron which is there on the another nitrogen atom will not be involved in the aromatic state. So this is all about aromaticity of benzene and benzenoid compounds. So this we have covered already in the next lecture. Just we have revised here. What is the aromaticity? What are the rules behind aromaticity? That's much I am going to revise from this lecture. Now we are proceeding further for the next part of the same chapter, that is substitution reaction for benzene. Okay, now already we have discussed that benzene is going under for the every time on the for the substitution reaction, benzene and benzenoid compounds will not go for addition reaction. The reason behind that, benzene is going to have too much conjugated structure. He is not going to allow the entry of another compounds, another groups inside the ring. They are going to hinder the entry of another compounds inside the ring. So they are always going for substitution type of reaction. And why electrophilic substitution type of reaction? We will see the reason behind why benzene is going for electrophilic substitution. We have already seen that the characteristic reaction of benzene involves only substitution. Either one of the hydrogen atom of benzene will substitute with the help of substituting groups. Now What kind of reagent bring about this substitution? Means which reagents are go for substitution inside the ring? What is the mechanism of these reactions? How they are substituted above and below the plane of the ring of the benzene, as there is a cloud of pi electron. We have seen the structure of benzene. There is upper part cloud of pi electron of p orbitals, as well as lower part of the cloud of electron below the plane of the ring. Because of resonance, these pi electrons are not involved in holding together the carbon nuclei than the pi electrons of carbon-carbon double bond. Still, in comparison with the electron, these electrons are loosely held. The electrons, the pi cloud of electrons, these electrons are generally loosely held as compared to sigma electrons. Now, it is not surprising that in its typical reaction, the benzene rings serve as a source of electron. Already we know that benzene is conjugated, benzene containing 3 number of double bond, that means 6 number of pi electrons. The all p orbitals of carbon atom is going to have one electron in each. So benzene every time it is going to serve as a source of electron. म्हणजे त्याच्याकडे electrons आहेत. They have that. The compounds with which it reacts are deficient in nature. That means the carbon or benzene, the carbon inside the benzene are having the electrons. So to which compound generally they will react? They will react with those compounds which are deficient in the electron. So the compounds with which benzene is reacting, they are generally deficient in the electron because benzene is having lot much of electrons. So they will react with those compounds which are generally deficient in the electron, and that are electrophilic reagent because they have less number of electrons. They are deficient, and the compounds which are electron loving are known as electrophilic. So which type of reagent they are reacting? Electrophilic reagent or electrophilic, or those are generally acids. Just as typical reaction of alkenes, these are electrophilic addition reactions. So the typical reaction of benzene rings are generally what we can call it as electrophilic substitution reaction. So the reactions in which benzene is undergoing are electrophilic substitution reaction. These reactions are characteristic of not only benzene itself. This is not limited to only benzene. It's all benzenoid, but the benzene ring where it is found in any structure, indeed of many aromatic ring and benzenoid and non-benzenoid compounds, every time it is going for what type of reaction? Electrophilic substitution reaction. Means not only benzene, any structure in which benzenoid compounds or benzenoid appear, resemblance structure is there, those are all going for which type of reaction? Electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reaction includes a wide variety of reactions. It is a n number of reactions are there in which benzene and benzenoid compounds will go for these type of reactions. What are those? Electrophilic aromatic substitution reactions. That are, already we have discussed this, that are nitration, halogenation, sulfonation, Friedel-Crafts reactions, and Friedel-Crafts reactions under this Friedel-Crafts alkylation and Friedel-Crafts acylation. Reactions like nitrosization and diazo coupling given or undergone by the rings which are of high reactivity means benzene and benzenoid compounds TJ काय आहेत? They are very reactive in nature. Undergone, they are highly reactive, means highly reactive benzenoid compounds will go for what type of reaction? nitrosization, and diazotopy. What are those? This we are going to see in forthcoming lectures. Now, and the reactions like disulfonation, isotopic exchange, and many ring closures, which although apparently and unrelated, these are found in closer examination, will be given by benzene and benzene. We are not interested in this. We are only interested in generally lower familiar compound, give a lower family of benzene compound will go for nitration, halogenation, sulfonation, Friedel-Crafts reaction. Friedel-Crafts reaction means what? Friedel-Crafts alkylation, Friedel-Crafts acylation. And those benzene compounds and benzenoid compounds which are highly reactive, those are going for nitrosization and diazotopy reaction. Now, these are some of the reactions. This slide we have already discussed in last point. So benzene is undergone which type of reaction? Nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. In this case, the AR belongs to any benzenoid compound, any aromatic group which attach directly to the ring carbon atom. So they are going to one of the hydrogen atoms. See how the structure is shown here. AR means any benzene or benzenoid compound and their hydrogen. So ARH plus nitrous acid in the presence of sulfuric acid, there is formation of, if AR is belongs to benzene, nitrobenzene. If AR is belongs to benzene, benzene sulfonic acid, halogenation. If ARH plus there is formation of benzoyl chloride, benzoyl bromide, alkyl benzene, and there is formation. Now, when there is acylation reaction, we have already seen that they are going to form a ketone. These reactions we are seeing in detail in next part. Now, what happened or how the substituent group? What are the substituent group? These are nitrous, sulfur, chlorine, bromine, alkyl chloride, acyl chloride. These are all substituent group. Now, how they are react? At what position they will react? This we are going to see. A group. Now, some of the terminologies are there. Before that, we will discuss some of the terminologies. What are those? A group that make the ring more reactive than benzene is called as activating group. Now, out of this group, any group which is involved in activation of the benzene, which will make the benzene ring active, which will make the benzene ring to favor the reaction, which will make the benzene ring more very reactive. Those compounds are known as activating group. Any group, whether it is chlorine, bromine, methyl group, nitro group, sulfur group, sulfide group, any group, if these groups are involved in activation of that benzene ring, which will increases the reactivity of that benzene ring, those groups are known as activating group. A group that make the ring less reactive. Any group which will decreases the reactivity of that benzene group, this is known as deactivating group. It is going inside. Those groups which will make the benzene ring more reactive, अशा groups ना काय म्हणायचं? Activating group. The group which will make the benzene ring less reactive, those are known as deactivating group. And a group that cause the attack to occur cheaply at the position. Which position? Ortho and para position. We know if the benzene structure, the first two carbon atoms are ortho position. The carbon atom which is there as the third position and fifth position are met up, and the carbon atom which is there at fourth position, we can call it as a para position. This you have already discussed in 12th. Or you know, a group that causes attack to occur cheaply at position, ortho and para, to it are called as ortho-para reactors. So, a group which is very specific one will react only those positions that are ortho and para. So they are specific in nature at ortho position and para position. So those groups are known as ortho and para director. A group that causes attack to occur cheaply at position, which position? Very specific, third and fifth position, that is meta, it is called as meta director. So what are these terminologies? A compound which is activating the benzene ring or which is converting the benzene ring into an active ring is known as activating group. A compound which is decreases the activity of the benzene ring is known as deactivating group. A group or a substituent which making the attack specifically to the ortho and para position are known as ortho or para director, and a group which will specifically attack on the position meta is known as meta director. Now, how we can determine the orientation? What is this? What is the meaning of this heading? How we can determine whether any group which will be acting on ortho position or meta position or para position, how we can determine? To determine the effect of a group on the orientation, in the principle, the compound containing this group attached to the benzene ring is allowed to undergo substitution and the product is analyzed for proportion of 3 isomers. So generally, एक तरी काय होणार आहे, a benzene compound or that substituent will either attack on ortho position or meta position or para position. This is final. Either they will attack on ortho or para or meta position. So they are going to form a isomers. What isomers? Ortho isomer, meta isomer or para isomer. So they are going to form a identification of each isomer as ortho, meta or para generally involves a comparison with the authentic sample of that isomer which is prepared by some other meta from a compound. Now what are these? So these are some of the substituents shown here which are directing either ortho or para, ortho plus para or meta director. So this is a percentage value how they are attacking on that benzene ring, ortho or para, both ortho and para or meta. So these are the 7 groups of function, that is hydroxyl group, bicarbonate, amide, methyl, then fluorine, chlorine, bromine and iodine. Now what is the percentage of every hydroxyl group? Approximately 50 to 55% will act on ortho, 40 to 45 to 50 by para, but 100% it will be acting on both position, ortho as well as para. So this hydroxyl group will occupy ortho position as well as para position simultaneously, but it is not going to occupy the meta position. The amide functionality will be acting on very chiefly, very lessly on the ortho position, but more about para position. And if we can compare, or we can do the substitution on both ortho para, it is 28%. Similarly, all of these. So generally, these all 7 family of compound will acting at both position, ortho and para, and they are remainingly or lessly cheaply acting on at what position? Meta position. This is a first series of compound which are directly or generally acting on ortho and para position and cheaply on meta position. But second group of compound or second set of compounds, second set of substituent, nitro, dimethylamine, cyanide, acid functionality, sulfonate, aldehyde. So these are all cheaply reacting on ortho para position, cheaply reacting on ortho para position, but majority of the cases they are acting on